everyone, welcome back to your YouTube channel. I'm Ziba, and today we're diving into the fundamental topic in calculus, which is the limits. Now, before we get started, if you're new here, please make sure to hit that subscriber button and ring the notification bell so you will never miss out on our math field adventure. Our topic for today is unlocking the secrets of limits in math. Limits are a crucial concept in calculus that not only form the building blocks of advanced mathematical ideas, but also find application in real world. In this video, we will break down the basics of limits, explore how to evaluate them, and even apply them to real world scenarios. So whether you're a student navigating the intrinsics of calculus or just someone curious about the magic of mathematics, this video is just for you. Okay, so if you're here on a quest for knowledge, do consider subscribing to our channel. We are on a mission to make math accessible, enjoyable, and most importantly, understandable for everyone. Hit that subscribe button and let's embark on this mathematical journey together. Now let's delve into the fascinating world of the limits. So today's agenda for this class is the introduction to limits. I want you at the end of the class to be able to define the limit in informal and formal way. What is the limit notation, the concept, and then two-sided or one-sided limit, and then visualizing it or graphing it, and the geometric interpretation. So the class objective, as I just mentioned in the previous slide, is you have to, at the end of this video, you have to be able to define what is the limit, what is one-way limit, two-way limit, and what is the notation, and how from the graph you could find the limit. Okay, so let's start with the very basic definition of a limit. So in calculus, the limit of a function is actually a fundamental concept that it tries to define the behavior of a function as the value, the x value, which is the input value, approaches a certain point. And that certain point could be, in most cases, is a point that the function is not defined. If you remember, we had when we had a fraction in algebra, the r fraction was not defined, where there was actually where the denominator was 0. So here, as you can see, for this specific fraction, this value x equals 0.4 makes the denominator what? 0. And at this point, the function it's not defined. So points which are not defined are very important for us, because we want to know what is the behavior of the function around this point. And that's the main reason that limit was actually introduced, to see what is the behavior of a function around the points in which the function is not defined. Well, actually, it doesn't. To talk more generally, it doesn't. The point doesn't need to be undefined. It could be any point, but most of the time, when we're talking about limits, we're talking about the points in which the graph is not defined and there is a hole, okay, in there. So let me show you what I mean from a graphic point of view. Maybe it makes it more easier to comprehend. So take a look at this continuous graph, okay, the blue one. What I mean by continuous, let me define it first. A continuous graph is a graph that you can graph it without actually lifting up your pen. So you can see, if I start from the one end and do my graph, I don't have to lift up my pen till I get the end of the graph, right? And then the domain of this function is from -3. See, the domain is related to the x value. So it starts from -6 all the way to +11, right? And the range is from -3 all the way to +4. Okay, these are the characteristics of our function. Now, As once more, this is a continuous graph, and we want to see what are the limits. If our function, right, this is the notation that we use for limit, right? Limit of a function in terms of x when the x is getting close or approaching to -3. Actually, this one was also I the notation was also actually introduced in the previous slide. This is the general form. So the limit of a function in terms of x, which could be any variable, and then the variable is getting close to any point in the graph, it's equal to an output. And we want to calculate the output. So here, for this continuous function, the limit of the function. So this is a function f of x. I don't know what is the equation, but I have the graph, right? So I want to see when x is getting close to -3, what is the output value? So when x is -3, exactly at this point, your graph is defined. And when x is -3, the y is exactly 0. How about the second one? X is getting close to 2. So at point 2, when the x is it's actually 2, your output or the y value is 4. The next one, x is getting close to 8. So when x is 8, right, the output would be -2. All right. Remember, guys, that is a continuous graph. And remember, even though it's continuous, there are no holes, or there are no discontinuity point on the graph. We still can define the limits, right? But these type of graphs with this continuous point in them are of a greater importance to us, especially when we talk about the limit theory. So what I mean by discontinuous, it is the opposite of continuous. So as you can see, when I want to do this graph, right, I go all the way. At this point, I have to lift up my pen, then go back again at here, and then lift it up again, continue here, then lift it up again, continue here, lift it up again. So you can see a few times I had to lift up my pen. Whether you're lifting up your pen once or more than once, it makes the graph discontinuous. And here, the point of discontinuity is of real importance to us. And most of the time, we define the limit for the point of discontinuity or holes. Okay, so as you can see here, there are some holes in your graph. When there is a hole in your graph, that means your function, it's not defined around those points. So at this point, we were discussing about this graph, which has got this discontinuity point. And then, as you can see, these holes, I call them a black hole, because when you have a black hole in real life, you don't want to get into it, right? You just want to go around it and study it. The same applies to here, right? Like when you have a hole in your graph, you don't know what's happening at that point, but you can just go around it and see what's actually happening there. So I call it a black hole. See, in this graph, you have 3 black holes, and these are the discontinuity of your graph. So x at 0, at 1, at 2. But then take a look at, and this function, it's called g, so g of x, and you could see that at point of continuity, your function is perfectly fine. So when it's -2, right, if your input is -2, your output is 0. If it's -1, your output is 3. And if it's 0, it's 1, right? But again, here there is a hole. So this is a particular case that we will discuss later on. Moving on to another point, another graph with how many points of discontinuity? 1, 2, kind of 3 and 4. So again, here you have 4 points of discontinuity of your function, which of f of x. And here we can define the limit theorem, the limit for not only the discontinuous, the holes, but also like regular point. So if f it's -3, right, there's a hole. If f is 4, well, your function is defined, you can easily report the y value, which is 2. F is 5, so the output would be 3. But f at 6, can you see on 6 there is like an asymptote here, so your function is not defined. F of 0, see here at point 0, here there's a hole, but here it's defined. Okay, this is the similar to that case that we just discussed. I leave it for later. And then f of 2, again the same thing. So there are three different types of scenarios: the points which are continuous, perfect, behaving like these part of the graph; the point when there is a hole, and at the same time there is a point which is defined; and then the third type of points which there is a completely hollow area, hollow point. So let's see what happens. Look at the other graph. This is one of my favorites, right? So this, the whole thing, the two parts are part of one graph, are part of one function, which is called f of x. Okay, so your function, it's called f of x, but it has two separate parts, so it is not continuous. Because see, if I want to move on my graph, I start from the end, then till I get here, then I have to lift up my pen and then move here, right? So this graph, it's not continuous, it's discontinuous. Okay, and consider this this actually green line to be like a wall. Okay, so there is a line, or there is a wall at x equals 5, and let's see what happens. So if you're an observer, okay, so now we were talking about this discontinuous graph, and I made this thing so you could understand. Like, look at these two guys standing on both sides of the wall. This is the wall, remember, this is the line. I said like this line, it's like a wall, so they can't see the other side. So this guy is asked, what is the value when what is the value of the red part of the, actually this part of the graph, when it's getting close to 5, right? So he can only see this side of the graph, so he says 3.8. The other guy, which is on the other side of the graph, he's asked the same question: what is the value when the x is getting close to 5? And then he reports 1.3. Okay, so one of them is reporting 3.8, the other one is reporting 1.3 around one specific point, which is x5. So as you can see in this case, okay, we showed this a as positive because we are approaching from the right side. Okay, because we are approaching from the right side, and this is the notation we use. We say a plus. If we are approaching from the left side, we show it with negative. Okay, this is the right, this is the left. Okay, so we show it with positive and negative. Or sometimes we call this the right limit, this side we call the left limit. As you can see here, the right limit, it's not equal to the left limit. So in this case, we call that the function, whatever this function is, around this specific point, which is x equals 5, doesn't have any limit. In other words, the limit of f of x when x is approaching a doesn't exist. Okay, this is a very, very important slide throughout this presentation. I want you to take a look at it again. Try to understand every single notation. What is the right limit, left limit? What do we mean when there is no limit? Okay, now So far, we did 3 or 4 different graphs, and we were trying to define limit from the graphical point of view. But let's try to see it from a different angle. So this is another function, which is x squared minus 1 divided by x minus 1. As you can see, the denominator, right? It's x minus 1, which is kind of causing problem because at x equal 1, there is a hole. Remember the hole? That means around this point, your function is not defined, okay? So we want to approach it from either side, let's say right side and left side, and to evaluate the right limit and left limit, okay, and see if the two values are equal or not. So let's say x, the point of discontinuity is around 1, so I approach it from left, starting from point 5. I try to get closer, 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 right? So point 0.5, point 0.9, point 0.99, and then I get so close to 1, but never actually get to 1, right? And then I plug in the x value and find the y value. You could see that as I get closer to 1, the value of y gets so close to 2. Now, let's approach the same point from the right side. Let's say I start at 1.5 and get so close to 1, but I never get into 1. I get so close. I approach 1, but I get so close to it, and then I will see that the y value also gets so close to 2. So as you can see, the right limit it's equal to the left limit, because here you can see that the final value of the right limit is equal to 2, and here the final value of the left limit is also equal to 2. So in this case, you could say that for this specific function, the left limit is equal to the right limit, and it's equal to 2. So around point x equal 1, the function does have a limit and it's equal to 2. In the next video, I will continue with the numeric or mathematical solutions to limit. So folks, I want you to stay around and watch the other videos in this series, because this thing it's not doesn't end here. In the next part of our series, as I promised, we will be delving even deeper into the advanced limit concepts, tackling challenges problem, and maybe even uncovering a few mathematical surprises. Okay, so please make sure you subscribe and have that notification bell on, because you don't want to miss any of the math adventure. So I want to hear from you. What other math topics or specific question do you have? Drop them in the comment below, and who knows, maybe your suggestion might just be the inspiration for our next video. Thank you for all joining me today. Until next time, keep exploring, keep learning, and remember, math is an incredible journey that we are all on together. See you in the next video.